Good afternoon. It gives me real pleasure to invite Professor Jasjeet Singh Bagla for the colloquium today. Uh, uh, it was actually scheduled a few times earlier and cancelled and accumulated enough time delay. And it's befitting that he's giving the colloquium on the Founders' Day. So Jasjeet, who I know for a long time, has worked on, he's a cosmologist and worked on a variety of topics in cosmology. He did his PhD from IUCA, and then he had two postdoctoral stints in Institute of Astronomy in Cambridge and Center for Astrophysics in Harvard. After that, he joined the HRI, Harishchandra Research Institute in Allahabad, and from where he joined ISAR Mohali, where he's still now. And he's got a very interesting title, Exotica and Gravitational Lensing, and we really look forward to what he has to say. So, Jasjeet.
Thank you. Thanks, Biman. Thank you for the kind invitation and for the patience for the various postponements of the trip which happened almost a year. I'll be talking about Exotica and gravitational lensing, and I'll explain what I mean by Exotica over here. So, if we look at developments in gravitational lensing, then the earliest written down calculations date back to 1801, although it is conjectured that Newton had done the same calculations, but he did not like the numbers, and therefore he did not write them down. He was asked pointedly by someone that will light be affected by gravity, and he just left it at saying that experiments will tell. And the reason probably was that he had done the calculation and he knew that the deviation which is expected is so tiny, it's of the order of micro arc seconds due to Earth's gravity, that it will not be easily detectable. Soldner did the same calculation in 1801, and the calculation becomes possible in Newtonian gravity because the mass of the particle which is moving, that drops out unless that happens to be zero. And in Newton's corpuscular theory of light, light was supposed to be made of particles, but the mass was not known. And so Soldner essentially happily cancelled the mass from both sides and did the calculation, found that the deviation of a light beam in Earth's gravity would be of the order of a few micro arc seconds. So horizon to horizon is 180 degrees. 1 by 3,600 of a degree is an arc second, and you are talking about roughly a millionth of that. That is the kind of deviation which you expect. He repeated the calculation for Sun, and he found it to be of the order of an arc second. He was disappointed. He published his work and left it at that. There was no follow-up for a very long time, presumably because at the same time as Soldner was doing his calculation, Young did the Young's double slit experiment, and the whole paradigm of light shifted from being a particle to a wave. And people didn't really know enough to be able to calculate how the wave would deviate from a straight line approximation. Einstein in 1911 revisited the problem from the perspective of equivalence principle, and he reproduced the same numbers as Soldner had got, and his estimate was slightly under an arc second for deviation around the Sun. He was excited and he wanted this to be measured. He started contacting astronomers and observatories, and in discussions with them, he realized that the only possibility is to look at stars during a total solar eclipse. So then he started asking a more pointed question: do you have plates, photographic plates from earlier solar eclipses where this could be measured? And nobody found anything really useful over there. He persuaded some astronomers to undertake a mission. In 1912, a mission went to Argentina for making observations of a total solar eclipse, which was completely rained out. In 1915, several expeditions were sent, although the measurement of deflection of light was to be done only by the German group, who were aware of what Einstein had been doing. They all went to Crimea. only to discover that the World War has started, and they were all told to leave their kit and go back, except for the German astronomers who were arrested as prisoners of war and later on exchanged with other people. So, and it's sorry, that was in 1914. In 1915, Einstein revised his estimate after getting the full general theory of relativity and found that his answer now was twice of what he had estimated earlier. He published it, but because the World War had started, most people outside of the Axis nations were not aware of what he had done because they did not have access to his papers. Some physicists in neutral countries like Netherlands, particularly De Sitter, was looking at what Einstein was doing, and he was writing letters to Eddington to inform him about what Einstein had calculated. Not the full calculation, but a summary. So Eddington got interested in this because he realized that the moment you have a finite speed of light and a maximum speed of transmission of any interaction, then Newton's theory of gravitation has to be modified. So he knew that there is a need for a field theory for gravitation, and Eddington essentially re-derived GR on his own because he did not have access to what Einstein had done. And he persuaded astronomers in England of the need to set up an expedition. Dyson, who was the royal astronomer at that time, he was persuaded, and he said that the eclipse, which will happen in 1919, May 29, 1919 to be precise, will be most opportune for two reasons. It's one of the longest total solar eclipses on record, and it was going to happen in the constellation of Taurus, very, very close to the Hyades open cluster. So therefore, you have plenty of stars with which you can do the measurement. Two stars particularly, a visual binary, were expected to be close to the limb of the sun. So they started planning in 1917, and finally observations were made from two locations, Principe off the western coast of Africa and Sobral in Brazil. And they reported their results in 1920. It was published in 1920. They actually reported it to the Royal Society and Royal Astronomical Society in November 1919. And they validated Einstein's prediction and showed that the observations were not consistent with Newton's, the other equivalence principle or Soldner's predictions. Campbell and Trumpler, they improved on this particular measurement in a 1922 eclipse, which happened in the Northern Territories in Australia. So whereas Eddington and Dyson and all had only a handful of stars with which they could make the measurement, Campbell and Trumpler used many tens of stars to improve upon that measurement. Unfortunately, after that, people essentially gave up on using eclipses, partly because it is fairly hard and you are at the mercy of weather all the time, and total solar eclipses happen in very often, they can only be seen in very remote places. And Einstein's theory had come to be accepted by that time. The next mention of gravitational lensing, apart from a few attempts made by Eddington and others to observe gravitational lensing by white dwarf stars and remote stars, is by Zwicky in 1937, where he proposed the use of gravitational lensing to measure the mass of clusters of galaxies. So Eddington had encountered this problem, that he was observing what looked like groups of galaxies in the sky, which seemed to be almost at the same redshift, and he conjectured that these were systems of galaxies which were in some kind of a dynamical equilibrium. But if he assumed a dynamical equilibrium, then he could estimate the mass using Virial theorem. That mass came out to be much, much higher, about 100 times higher than the mass of all the stars in all of these galaxies. Okay. So there was a deficit, and he didn't know how to go around it. So he's, in the paper, he lists 3 or 4 different ways in which this can be cross-checked, and gravitational lensing is one of the proposals that comes up over there. There were theoretical calculations which people did, but observationally, the next milestone is after 1937 is 1979, when the first observation of lensing of a distant quasar by a galaxy was done. And it took so long because the gravitational lensing is actually very, very weak. Bending of light is by a very, very small angle. And as a result, if you want to see multiple images, you can see this only for very distant sources, which naturally will be very, very faint. So you needed a very, very high sensitivity. And that became possible with the advent of charge coupled detectors, CCDs. And because CCDs had a quantum efficiency of 80 to 90% compared to photographic plates, which had an efficiency of around 10%. So your sensitivity increased by more than a factor of 8 for the same instruments, and that is how this particular measurement became possible. So this is a crash course on how gravitational lensing has become a part of astronomy. The framework in which we interpret gravitational lensing is that we have a concentration of mass in between a source which is far away and the observer, and the bending of light, which is highly exaggerated over here. The bending of light by this concentration of mass causes geodesics along different directions to focus on the observer. So as an observer, you begin to see multiple images of the same source. When I say that the bending is highly exaggerated, that's because over here the bending is shown by about 20-30 degrees, whereas typically it is of the order of a few arc seconds, if you're lucky. And the bending is essentially 4gm by bc square, m being the mass enclosed inside, and b is the distance of nearest approach. You might think that 1 by the distance is like the gravitational potential, but because typically the scale of this massive object is very, very small compared to all the other lengths which are involved, we like to mathematically think of this as all the mass being concentrated in a thin sheet in between the source and the observer. And in a plane, 1 by the distance is actually the gradient of the potential, because in 2 dimensions the potential will be logarithmic. There are many regimes of gravitational lensing. Incidentally, we are talking about gravity in the weak field limit, because we can take the approximation, approximation of the gravitational potential divided by speed of light square, c square, being much, much smaller than 1. Within this weak field limit, we can have many-to-one mapping, which is called strong lensing, and one-to-one, which is weak lensing. So to give you a simile, this is a picture of a swimming pool. The bottom of the swimming pool has tiles, which are square tiles. And you can see that some of these tiles appear very, very distorted, but each tile appears only once. Okay, so the shape is distorted, but each tile appears only once. That is one-to-one mapping, and it would be weak lensing. But there are places where everything is kind of jumbled up, or you can see multiple images of the same region. This would be strong lensing. Mathematically, it is easier to model it as a map from the image plane, so what you are seeing, to the source plane. And we will all the time talk about gravitational lensing in those terms, as a map between a 2-dimensional image plane to a 2-dimensional source plane. To make it more quantitative, if I have an observer and a lens, so I have this axis joining the center of the lens to the observer, extend it further, and I have a source which is offset from this line, then eta, which is this length, can be written in multiple ways. One is the angle beta, which connects directly to the source into this distance between the observer and the source, but also as theta into ds. So theta is where I am actually seeing the image after bending, into this, minus the bending angle into the distance between the lens and the source. So again, small angle approximation all through. This gives me what is called the lens equation, which can be written like this. So beta is an angle in the image, in the source plane. Theta is a corresponding angle in the image plane. Whenever I have multiple solutions for theta for a given beta, I will see multiple images. And the bending angle alpha can be written as gradient of the two-dimensional gravitational potential over here. So, as I said, we will consider lensing as a map between a two-dimensional image plane and a two-dimensional source plane. Mapping could be one-to-one or many-to-one. Magnification is essentially the change of area element in this mapping. Because as you know, the specific intensity is preserved along a geodesic. So, the total flux which I receive from a source is going to change only because the projected area of a source on the sky has changed as a result of this lensing. And of course, for many-to-one mapping, one has to sum over all the images. Now, in this map, it's possible that a finite area from the image plane maps to zero area in the source plane. When that happens, magnification is infinite. But that's a formality because all sources have a finite area, and when I average the magnification over the source area, the magnification will always turn out to be finite. But one can sense that if I have a smaller source, I can achieve much higher magnifications than I can for a larger source. So the set of points in the image plane that correspond to infinite magnification, they form what are called critical curves. I will show you examples of that. And these curves, when mapped to the source plane, they are called caustics. And of course, this mapping has to be done differently for each source distance and hence each source plane. So this is an image from a simulation. On the right-hand side panel, you are seeing what you would observe in the sky. On the left-hand panel, you are seeing how the source is actually located. The red and the green curves on the right-hand side, these are the critical curves. So if I had a source on this curve, that will get mapped to a location on the corresponding curves on the source plane. And for a point source, the magnification would technically be infinite. Here you see that the source is actually outside of caustics, and I have a one-to-one image, one-to-one mapping, except that the image is slightly distorted. It is kind of stretched in one direction, squished in the other. If I put the same source on one of the caustics, I see that now I have multiple images for that part of the source which is inside the caustic. I am seeing this creation of a pair of images. Go further. So the region which is inside green but outside the red caustic, I am seeing 3 images, 1 outside, 2 over here. Region which is inside the red caustic, I am seeing 5 images, 1, 2, 3, 4, 5. So there is this creation of a pair of images which is happening over here. And the images which are being created are actually mirror reflections of each other. They are parity inverted. If the source is perfectly aligned, notice that in this particular simulation, the lens model was taken to be elliptical. It does not have circular symmetry. And you get some kind of a ring, and we will get to the significance of that ring. So there are 4 images in the ring and 1 at the center, which is highly demagnified because the area is shrunk. Okay? So this is the faint image, and these are the brighter images. To gain some more insight into this mapping, let's look at what happens for a point mass lens. So in that case, the bending angle is basically 4 gm by c square into the distance, which I can write in terms of the angle theta. So I have theta appearing twice, this becomes a quadratic equation, and I can write it in this form. Yeah. Notice that if theta is equal to 0, then beta has to be 0. Or if theta is equal to theta e, which is written over here, then again beta is 0. So if the source and the lens and the observer are perfectly aligned, you are actually going to see a ring of images, which is called the Einstein ring, and this is the size of that ring, theta e. Magnification at any location is given by essentially the Jacobian of this transformation, and that is given over here. So on the right, I show example of microlensing by a black hole, which is about as close as you can get to a point mass lens. On the x-axis, you have time in days, and on the y-axis, you have the observed flux from a distant star. So people observed, and this observation was done in 2011, that the flux went up and then it came down. So what is happening over here? We have the lens, and there is the Einstein ring, and the source is passing behind the lens. So I can take multiple ways of looking at it. I can fix a line between the observer and the source, in which case the lens is moving, or I can fix the line from the observer to the lens, and then the source is moving, but it is essentially a question of relative motion. So as the source is moving, it comes closer, and as it comes closer, the magnification goes up. Okay? And therefore, we have a peak in magnification, and hence the flux received. While these observations were done in 2011, at that time the distance to the star which was being magnified was not known. That became known only in 2018 with the Gaia observations. And once the distance was found, one could plug in that distance into these equations and ask what kind of a mass, intervening mass, would have produced this. So that is when people realized that the intervening mass has to be at least 6 times the mass of the sun. And because no star was seen over there, going fairly deep in terms of sensitivity, they realized that it was a free-floating black hole somewhere in the Milky Way. Okay. If I go to more distant sources, then this is a near approximation of an Einstein ring. In this case, the lensing is being done by this red galaxy in the middle. This is called luminous red galaxy. This is a Hubble Space Telescope picture. And the distorted galaxy is a background galaxy which is much further out. If I don't have a symmetry of a point mass lens, which has an axial or a circular symmetry, in that case, we don't really have any spectacular ring kind of a structure, but you will see arcs like this, and so on, or the one over here. So these are from the earliest observations made by the James Webb Space Telescope more than 2 years ago. What you can infer from here, very naively, is that the radius of curvature of these systems of arcs is, if you take it to be approximately equal to some kind of an Einstein ring radius, then you can estimate how much mass is there. So this brings us back to what Zwicky had conjectured back in 1937, and this method has been used not in the naive way in which I am saying, but with more detailed modeling. This method has been used to estimate masses of these clusters. Okay. Now in gravitational lensing, there are multiple types of image structures that can form, and I showed you snapshots from this particular simulation. Let me show you the full animation now. So here the source will kind of move in. So this pointy part is called a cusp. Otherwise, rest of the caustic is called a fold. Whenever you cross a cusp, you have generation of a pair of images which are very close to each other. Fold also does something similar, but the magnification variations are different. These are the only stable image formations which can happen in gravitational lensing in image plane to source plane model. However, there are unstable image forms that can happen, and the analysis of that has been done on the basis of what is called catastrophe theory. So this modeling was done in a slightly different context, but same mapping by Arnold, Shandarin, and Zeldovich back in 1980. And they found that there are 3 unstable image types which can form. As you saw from the earlier slide, the first distant lensing which was observed was in 1979. And even today, the total number of lens systems which are known are in a few hundreds. So most of the focus has been on studying lensing at what you call a fold or a cusp in terms of caustics. About 25 years ago, I started looking at it and wondering as to what will happen if you go and study the unstable types of image formations. For that, I'll give you a little bit of mathematics here, and then we'll go away from equations. So this is just a review. We have the lens equation. Bending angle is given by gradient of a potential. And the area element transformation is given in terms of the second derivative of this potential. And it's all in 2 dimensions. So since this is symmetric, I can always diagonalize it. So the magnification can be written as 1 by the determinant of this transformation. And because it is symmetric matrix, I can find eigenvalues. And I'll have 2 eigenvalues. And I'll have a stretching factor, which is just the ratio of 2 distances. This particular 2 by 2 matrix can also be written in terms of what is called the convergence, kappa, which gives you the overall magnification, and shear. So there are 2 components of shear, gamma 1 and gamma 2, which tell you about how the images will get distorted. Kappa will just either talk about concentration or dilation of the overall image. Cusp and fold correspond to those situations where one of these 2 brackets goes to 0. Okay? Now, it turns out that the unstable image forms are such that there is one unstable image form where one of them goes to 0. That is called swallowtail. We'll come to that in a short while. The other is where both of them go to 0 simultaneously. So that is the degenerate point where the 2 eigenvalues are equal. Those points are called umbilics. So the first system which we studied was hyperbolic umbilic, and I wrote about this in, I think, in proceedings about 25 years ago. So here, the degenerate point is here and here. So there is a pair of these which occurs in every elliptical lens system. And what you find is that if the source is sitting at this point, at the critical point, then you get a ring of images, except that this ring of images has a radius of curvature which is very small as compared to the Einstein ring radius. Einstein ring over here would be like this big, whereas this is very small. And to understand the unstable nature, when I run through the simulation, you will see that unlike the other one where the spectacular images were forming and staying for a long time, here they will form and disappear. So mathematically, these are considered unstable because if I take a lens model which has this kind of an image, exotic image, then if I perturb the lens model a little bit, this particular singularity may just disappear. Okay? So this is a hyperbolic umbilic, and at that stage when I asked observers, they said, no, we have never seen anything like this. And I kind of let it be for a while. In 2007, one system was discovered. This is Abel 1703. So this is the large arc which gives you the idea of the Einstein ring radius. And there is this tiny system which is blown up over here and shown. So then I started some analysis again. And within year or so of that appearing in press, a theoretical analysis appeared in 2009, which said that these are going to be so rare that you will see at most one such system in the entire sky. We have seen one, it's over, no more excitement. But one of my students, master's students in Mohali, they were interested and they started doing some analysis. And then later on, it was followed up by a PhD student. And we discovered that this estimate was a gross underestimate. So this is the other kind of degenerate point. The other earlier one was hyperbolic umbilic. This is elliptical umbilic. This has never been seen. And in our analysis also, this is the most unstable of the three exotic types. So if you ever see an astronomical image with this formation, which will appear for a short while, alert me. So you have a triangular formation of images. Now, unlike the hyperbolic umbilic, which technically is present in every elliptical lens, this requires at least a two-component lens. Okay? So this is definitely going to be much rarer. The third I mentioned is a swallowtail. I will not go into the details of exactly how it appears, but I mean the genesis of it. But it gives rise to an arc of 4 images, which is very, very straight. So the hyperbolic umbilic had a ring-like structure, which was very, very tiny. Elliptic umbilic had a triangular structure. This one has what is a nonsense statement of straight arc. Okay, this was first observed about 26, 27 years ago in Abel 370. Now we know of several other instances. So this is, it's also called a dragon's arc. Compare with this one and this one, which are gravitationally lensed arcs. So this was relatively straighter. These are not, these lines, other lines which you see are not gravitationally lensed systems. They are actually asteroid tracks because this HST image was made over a 3-week period. So in catastrophe theory, the definitions of these singularities are given in terms of derivatives of the eigenvalues and eigenvectors. So we decided to take mass models for gravitational lens systems and apply the classification scheme. So we wrote code where we could identify each of these image types. And then for Abel 370, where I just showed you the image, we took all the mass models which had been made by people, did the analysis, and to our horror, we found that the singularity maps looked very different. The reason for this is that some maps are made assuming that mass follows light, and they assign some mass for every galaxy which we see in the cluster, apart from overall mass distribution for the cluster. So it has a lot of small-scale structure, whereas other maps, like the one on bottom left, which is a non-parametric model, here you essentially assume a pixelated mass distribution and vary mass in each pixel independently of the light distribution to reproduce the image formation. So we found that the number of hyperbolic umbilics, etc., predicted for clusters of galaxies was very high if we use parametric models, but not so high if we use the non-parametric models. But what we found was that even with non-parametric models, we would predict at least one hyperbolic umbilic for every 5 clusters of galaxies, not one in the entire sky. We did this analysis in multiple ways, and the result is fairly robust. So we stuck our neck out and wrote it up, saying that the earlier estimate was incorrect. The other interesting thing which we found is that the time delay for umbilics and swallowtail. Now here you recall the earlier cartoon where the light ray is coming to us along different geodesics around the mass distribution. These two paths don't have the same path length. So if something in the source varies, I will see variation at different times in the 2 images or 3 images, and I can calculate the time delay for every pair of images. If we have a typical 5-image system, then the time delay is of the order of a few hundred to a few thousand days for clusters of galaxies which do lensing. But for umbilics, hyperbolic umbilics, we found that this was expected to be at most a few hundred days. And for swallowtails, it's up to 100 days. So it is much shorter. Why is this significant? Because these exotic image forms correspond to unstable singularities, the lens maps are determined to great accuracy in this neighborhood. And if the time delay for these images is not very long, then one can do this measurement repeatedly over the same time period. And this time delay can be used to estimate the scale of the universe and measure Hubble's constant. One might think that the same thing which people have been trying with galaxy scale lenses would help. But with galaxy scale lenses, typically the problem is that there is only one lensed source. So there is a mass sheet degeneracy, and the lens model is not very well determined. And those uncertainties creep into your estimation of the Hubble's constant. Whereas here, so we can turn the game around. Yes, these are unstable singularities of the map. But because they are unstable, your map is very well known at that point of time. You are seeing this singularity. And therefore, one can determine the lens map very nicely in these locations. And therefore, for cosmography, these will be very, very useful. I will come back to this point a little bit later. So in 2023, this paper by Lagatuta et al. Appeared. And they had done deep Muse observations of certain clusters of several. Here they presented results for one cluster of galaxies. And they found 3 hyperbolic umbilics in this one. So this is 1.1, 1.2, 3, 4, and then 2, tiny ring here, and then you have 10, which is here. So they found 3 hyperbolic umbilics in a single cluster, and actually they have observed many more. They are right now preparing an atlas of hyperbolic umbilics paper with about 10 to 12 sources. So this was really great news for us because we felt vindicated that more and more of these should be seen. So these are essentially critical curves showing essentially each of the images has to be in a different quadrant across these critical curves, and you see that over here. These are at redshifts of almost 3, almost 2, and just over 6. Spectra have been taken to verify that these are images of the same source. So what do we do with this? Well, what we can do with this is that unlike other gravitational lens system where you have an Einstein ring kind of a structure or you have an arc which is sitting somewhere, which gives you an idea of the mass enclosed in the cluster at a very large scale. Here you are observing these systems very close to the center. So you can do a very good estimation of the mass of the inner part of the cluster and therefore determine the density profile. Why is this useful? This is useful because there are many conjectures that the dark matter which we have may not be collisionless. And if it is collisional, then the inner core will be flatter, and therefore determining this is very, very useful. So they were able to push determinations from around a few hundred kiloparsecs down to about 20 kiloparsecs. And you can see that even in the projected distribution, the slope of the projected density is still somewhat cuspy. It's not flat. They were able to reconstruct the sources also. So one of the sources looks like a pair of dwarf galaxies or a galaxy with 2 star-forming clumps. So now that we know these systems, we can go back and do the time delay estimations. So what we do for this is, yes?
When you talk about time delay, this is probably of some flare observed in multiple images. And how uniquely can one identify one flare seen in one image to another flare?
Yeah, so we're not thinking actually of flare, but thinking more of a nova or a supernova happening in one of these galaxies, in a source galaxy. Then you will have a long-term light curve, which will have which you know the structure for, for a core collapse.
Over supernova in the quasar.
In the source galaxy. So if you see, this is a galaxy with multiple star-forming clumps. So if somewhere in this galaxy one supernova goes off, that supernova will dominate over the galaxy for a period of time, and we'll be able to observe the light curve, and we'll get a different light curve for each of the images.
So not multiple flares, more like a single flare.
Yes. These are very distant. So for flares, etc., you will also need observations at a very high cadence. Otherwise, it becomes hard to observe. So we find, again, reinforcing that typically.
It's a rare rocket.
Sorry?
Supernova in a dwarf galaxy is a rare rocket.
Right. So supernova in a.
Reaches to see one in one particular.
Yeah. So you will have roughly 1 per 100 years per galaxy. And this is higher redshift, so it could be a little bit higher than that. But if I have, let us say, 10 to 12 such systems which are known to me, then observing them over a 10-year period, even observing once a month is enough. I'll pick up something. So the time delays are of the order of days, going up to about 100 days for different images. The last thing which I will cover in the talk is neutral hydrogen lensing simulations in Hubble frontier fields. So this is something which Tariq Blecher, Roger Dean and their group have been working on for some time, primarily looking at how to observe these using the Meerkat array and SCA1, which will come up later.
Jasjeet,
Yes.
so this time delay thing, isn't it often done for quasars as sources, right?
That has been done for quasars and supernovae with galaxy lenses. With quasars, you have a variability. And you try to look for same kind of variability and so on. Or if you have supernova, you try to match that.
Somewhat different game.
This is a supernova, but the main issue over there with galaxy lenses is that the lens model itself is not very certain. There are
So uncertainty of lens.
mass sheet degeneracy is there, and
So there's only one.
and you have only one lens source. Yeah. So what they find is that Abel 370 is the most promising system. This is the picture which I had shown you, and they gave predictions for 2-arc systems. Of course, they analyze a number of other clusters as well. So the upper one is for the Dragon arc, the swallowtail system which I showed you, and the lower one is for a different system of arcs in the same cluster. And these are for the curves are for different models of the lens. Notice that for the Dragon arc, they all converge. For the other arc, there is no convergence. So this is the point which I was trying to make, that the lens model for these special image types is determined very well. Even if you don't know rest of the field that well, that part has to be determined because these are unstable image forms. And Blecher et al. Find that an integration time of about 70 hours should suffice for a 5 sigma detection with Meerkat. We find similar numbers for the UGMRT. So we have been doing analysis for a catalog of around 70 clusters of galaxies, and we have found about 5 or 6 clusters which are very, very promising for this kind of a study. Abel 1703, which was the first hyperbolic umbilic which was discovered. This is in the northern sky. This is not accessible to Meerkat, but can be observed easily with UGMRT. We have done estimates over here, and we feel that SNR greater than 5 with the UGMRT in about 80 hours can be obtained. But what I've discovered is that right now GMRT has a little bit of a problem at the frequency where this line will appear, because a few companies have put up their mobile towers with extra high intensity transmitters at the periphery of the zone, because they are not allowed to put towers in the GMRT area. They have to be outside. But they have put very powerful transmitters over there, and 5G transmitters are cutting directly into the frequency where this line will appear. But they have some negotiations going on, and I hope that this will get resolved. We are also doing calculations for doing blind surveys for H1 in directions of different clusters. Now, main uncertainty is we don't know what are the H1 properties of galaxies at high redshifts. Only a few measurements have been made. We find that at redshift of around 0.35, 0.4, there is hardly any change from redshift 0. Whereas if you look at measurements around redshift of 1, both of these have been done with the UGMRT. The number of massive galaxies with large amount of neutral hydrogen, atomic hydrogen, is much higher. So this is the lower estimate in some sense, with the redshift 0.35 measurement extrapolated. In the leftmost panel, you have the source redshift here and H1 mass here. The color of these points, these circles, tells you the SNR. So focus on the yellow ones, and you can see that the likelihood of some high significance detections being made all the way to redshift of 1.2, that possibility exists. And the same data is represented in other ways. So this is with the similar estimate, but now using the measured or estimated H1 mass function at redshift of 1. Here, because you see many more galaxies with high H1 mass, the number of yellow circles increases. So we are trying to refine this estimate and make predictions for and propose strategies for what kind of observations should be made. I come to my summary now. One is that point singularities are very sensitive to details of lens models, and that is if you are kind of doing a theoretical projection. Observationally, if you have something, you can fix them very well. We estimate that many more umbilics and swallowtails should be seen than originally estimated. And recent observational discovery of 3 HUs in one cluster suggests that expected numbers are likely to be higher than even the most conservative estimates that we had given, which was 1 in 5 clusters. And aspects like time delay also make discovery and follow-up studies potentially rewarding for cosmography, as well as substructure in lensing. I did not go into the how one can use these umbilics for substructure, but I can get to that if there is a question. And targeted radio observations for lensed H1 in galaxies in band 4 of UGMRT should be within reach within about 100 hours of observations, both UGMRT and MeerKAT. Blind detection will require longer observations or luck, but such observations could potentially be combined with other science goals. So people who have contributed, Ashish Meena has been a major contributor. All the work which I have shown here, he was a collaborator. Swaraj Bharti is a current PhD student. Sonia Sharma is the one who kind of started digging into it early on. Collaborators, Lilia Williams and Agniva Ghosh. And I have gained discussions, had discussions on lensing and catastrophe theory with all of these people, Narasimha, Rajaram Nityanand, Kandu, Paddy, Sargi Shandaran, and Varun Sani. I'll stop here. Thank you.
Thanks, Jasjeet, for the wonderful talk, the glimpse of exotic samples of gravitational lensing. Questions?
Hi. Maybe a bit naive because I'm not from the field, but as I understand, the lens model and the inferred mass distribution is discrete.
No, it is not. It is smooth. So you basically assume that in the parametric models, you assume some kind of a smooth distribution for the cluster as a whole, plus a smooth distribution corresponding to each galaxy.
So how do you in the first place guess that? I mean, is it coming from what you observe?
Yeah, so you have
theoretically,
you have to vary these components to reproduce the lensing which you see.
But from the calculation or the theoretical point of view,
right.
Is there something that constrains this distribution?
Yes, it does. So what you do is, so theoretically we know that most halos have a Navarro-Franken-White kind of a density profile. So you take a projected version of that and you assign that to each one of the components. then you know that in clusters of galaxies, the gas distribution is for more or less a beta model. So you plug in that. So you borrow these things which are known from different bits to give the mass distribution.
Thanks.
The light curve that you showed for a galactic microlensing event with a foreground black hole, is that the only such event or there are several such?
No, that was the first such event. Then with microlensing, I don't know if they have found one more, but they have found one with astrometry, where they found a star which is in a binary with presumed to be a black hole. Yeah.
Okay.
But microlensing by a black hole, I don't know if there is any other.
And this is consistent with what would be expected number of
Still very low
field
numbers. It's expected
single
that
black holes?
Gaia next DR4 from Gaia, they might come up with more events. So yeah, no, there are various models for mass function of black holes in the halo, and what has been seen is not alarming. It doesn't kind of disturb anyone, but the numbers are still very, very low to kind of do a good comparison.
So, if I understand right, so this quasar galaxy thing, you said there's systematic uncertainty, right? Because you have, mass plane degeneracy, right? So, length sheet, whatever, okay. So, is the characteristic of that known? I mean, whether it tends to overestimate, underestimate, the uncertainty is large, but
Right.
is there a bias to it? I mean,
I have not seen any clear analysis of that. So there are ways. If you have, let us say, 2 or more sources, then you can get rid of that degeneracy. But otherwise, no. The other issue which I did not go into is that for a single lensed object, single lensed source, very often the ellipticity of the lens itself is very poorly constrained. So all of those things essentially add
right.
up.
So, yeah, no, I was just trying to see the H0 whole story going on.
Right.
So, because often what is not emphasized is the error bars, systematic and statistical.
Right.
No one seems to distinguish it, but they are different. So that I think is something. So now with your swallowtail or this hyperbolic
Umbilics.
arc, umbilics, yeah, whatever. So what have you made at least a rough estimate of how well you, if you see a couple of systems like that,
Right.
how well will you get the H0?
Yeah, so here what we find is that all the lens mass models agree very well over there.
Yeah.
Drawn up in completely different ways. They agree very well when it comes
So
to
that
singularity.
uncertainty, systematic
That
uncertainty will be
that is taken
small,
care of.
but then
Statistical will be high because you have fewer sources.
fewer lenses, yeah.
So it's a balance.
What's the value that you get?
No, nothing has been seen yet.
Okay.
Okay, but in the same system you can have both, right? Oh no, you can't have.
No. The only thing is now, like David and all, they are putting together an atlas of hyperbolic umbilic systems. We know that they have at least 10. We are putting together an atlas of swallowtail systems, where again we have at least 10. And JWST is doing a quick survey of 100 clusters of galaxies. Those models will become available in a few months' time. And in a sneak preview of that, we have spotted at least a couple of hyperbolic umbilics and swallowtails in that as well.
Yes.
So the numbers will increase, and hopefully one will be able to get somewhere sensible.
That sounds
Time
exciting.
delays you have observed, right?
Yes.
And from that time delay, what do you get?
No, but there is no time delay observed yet. We have
Oh,
not
okay.
seen any time varying thing
Okay,
in
okay,
this.
right.
I mean, they'll have a collection and then they'll have a waiting game to see which one lights up, right? So it's,
No, so for example, one of the things which is expected to be done with the LSST is that all such systems will be observed, let's say, twice a week. So anything which goes off, you will see it.
Any other questions? Yuri.
Thanks. As I understand, when you want to understand the interrelation, the correspondence between the sources, how they manifest in gravitational engine, and the numerical models,
Yes.
You have to apply there to numerical simulations a very high resolution in all senses, in angular resolution, sensitivity, and all these things.
So these are for observed systems.
Yes, yes.
So we essentially have to have high resolution images of observed systems
Yes,
and spectra.
that's right.
Right.
And then you model this,
Yes.
and you want to understand what is behind the lens.
Yes.
And you compare this model with the this your picture, the observed picture. What is required numerical facilities in order to reproduce it firmly? Particularly accounting that the cusps, they are very tiny in space,
Right.
in angular spheres.
Yes.
Can you describe these troubles very briefly?
Right. So if we look at the number of systems, so we have fold, we have cusp, and then we have umbilicus and swallowtail. So folds are about 10 times more in number than the cusp systems, and these are about 20 times more than the umbilicus and the swallowtail systems. So at present, the total known number of gravitational lens systems, galaxies plus clusters, is of the order of 1,000. With Euclid, it is expected to, the total number is expected to go up to about 100,000. And Euclid and JWST both give very good sub-arc second images. One needs to go down to about 0.1 arc seconds or better, and one needs to go down to about 28th magnitude in R or I in order to have enough systems to play with. And both Euclid and JWST are doing that. So we are essentially moving in that direction. Now, with JWST observations, it has become possible for the first time to do a joint reconstruction not only of the mass map, but also of the source structure. So that is becoming possible now. It was not possible to do that earlier. So we are getting there, essentially. Yeah. So JWST, typically the resolution which we are, the resolution at which one constructs the mass maps is 0.05 arc seconds. Yeah. Yeah. Yeah.
If there are no more questions, then let's thank Jasjeet again for the wonderful talk. Is there any height you?
Yeah, there is